Thank you. So thank you, Stefano, actually vocality, whom I am visiting for a month officially, for bringing me here in Florence. And the first time I in Pisa, and to still see this Leaning Tower of Pisa. So before that, let me, and also the organizers for the kind invitation to present in front of this community. So I'm going to talk about my latest work, which is on chromata oscillators, which many of you must be aware of. And the thing which is novel in my work, that is, I am going beyond this pairwise interactions. So for network science from last 25 years, have focused more attention on pairwise interactions, and I am going to tell what happens when you incorporate higher order interaction, and of course, in presence of adaptation in higher order interactions. Okay, and this work is in collaboration with two of my bright young PhD students, Priyanka and Ayushi. And yesterday I got a mail from the journal that is published in Chaos as a fast track article. So, okay. So you have, so let me first define this higher order interaction, that what does it mean? So networks that capture the pairwise interaction, for example, you have here a pair of the nodes, okay? And this is connected by a connection, and that is known mathematically as one simplex. And then you can think of now two simplex means now you have three nodes which are interacting simultaneously, and you cannot write down in the like pairwise components. So this is a two simplex. Similarly, this is three simplex where four nodes, they are interacting simultaneously. And the one very natural example which we can visualize such kind of higher order interaction is scientific co-authorship networks. For example, suppose if three authors have a written paper together, you cannot write that in terms of pairwise interaction. It's really the higher order interaction between the three scientists, unless and until they have written separate paper in terms of the pairwise. So that is a higher order. It's not the pairwise if three scientists have written a paper together. So that is the one very simple example of existence of such kind of higher order interactions in real world system. And there are many examples, which is there in this slides, like in ecological systems, which where you have more than three species. And this example, I remember when Stefano was visiting me in India in the car, my car, when I was driving him to the institute, he explained me actually this example of ecological system, where you have more than two species, they fight for the food or territory. And then you have protein interaction, spreading of consensus or contagious disease due to the community interaction. There also you cannot actually truncate the things or model that systems in terms of a pairwise interaction. So these are the certain examples. And here we have recent physics reports in collaboration with Stefano Boccaletti and myself, and there are other people, where we have written down the review of the structure and dynamics of the networks with the higher order interactions. So this is all for the introduction. And after that, let me come to my model. So this is my chromata oscillator model. And quickly, let me revise that what does it, like how this chromata oscillator that behaves. So you see, this is the chromata oscillator with the phase theta. This is only the phase of ith oscillator. And in absence of any interaction, it will just keep on revolving with this frequency omega I. And now when I add interaction, and this is the very famous, like in 1980s, Kuramoto wrote down his thesis, and more than 10,000 paper which got published actually on this very simple Kuramoto oscillator. And why? Because as you keep on increasing the coupling strength, here K is the coupling strength, N is the normalization factor. And right now I'm just talking about the pairwise. I have not still introduced this higher order interaction. But with the pairwise, as you keep on increasing this coupling strength, K by N, which is here lambda, one has this supercritical bifurcation, very smooth transition to the second order transition to the synchronization. And this is the rule, like those oscillator which deviate from their mean frequency of the entire system with this lambda R, they start coming into the cluster, and slowly the clusters rose up, and then you get smooth second order transition to synchronization. And here R is the order parameter. And quickly you can see that if all thetas are equal, it means if we are in the synchronized state, R is 1. And if thetas are homogeneously distributed between 0 to 2 pi, It means incoherent state, R is 0. So this is the measure of synchronization. So this is the state of art with the pairwise interaction. Of course, you get first order and all those things, but with the simple model, you get this simple second order transition to synchronization. What I do, I take same coupled Kuramoto oscillator, I put on the higher order interactions or the simplicial complex, and then I include also adaptation because this work has already been done. Last 3-4 years, a lot of work has been done on coupled Kuramoto oscillators on simplicial complexes. So this we have also done and some other groups. And now what is new here, that is we are going to put adaptation. And how? So now this simple pairwise interaction leads to the second order. Now what I do, I introduce now this higher order interaction. So now here you can see, here we have pairwise interaction. I is interacting with J. But in the second term, now you can see I, J, K. So there are 3 nodes which are interacting simultaneously. And we cannot truncate this interaction in terms of the pairwise because of this is sinusoidal function. This is nonlinear function. So now you have this higher order triadic interaction, I, J, K, which are interacting simultaneously. And it has been shown that as soon as you introduce this higher order interaction, instead of this supercritical bifurcation leading to the second order synchronization, you get actually here subcritical bifurcation, which leads to, this R is equal to 0 state becomes unstable and trajectory jumps to the far off state. And you get this kind of first order transition to synchronization. So this is the state of art in the field. What I do now, I am going to introduce adaptation in the following manner, very simple manner. There can be various other ways you can introduce adaptation. And right now I am focusing on only one ways of introducing adaptation through the order parameters. So here you can see if you have more coherence, like R is the measure of the coherence in the system, then it is giving the feedback to this coupling strength and it is becoming stronger. So this is the one very simple possible way of introducing adaptation in this kind of model. And what is there's few examples which I have written, like when you clap in the unison, so more and more people join and hear the sound of the clapping that works like a feedback. So, and that can lead to this synchronization transition and whatever. So this is one of the example, and the brain also connection among neurons that adopt based on their synchronization activities. Just a few example to motivate that what is the use of. And so far, so people have done in the pairwise, this has already been done. And this is a paper, I think this is also Stefano-Boccaletti TRL paper in 2015, where they have shown that as soon as you put this adaptation into the pairwise interaction, you get first order. So without adaptation is for second order, and with adaptation is the first order transition jump. But you know, in the several cases, real world system, there are this kind of first order transitions are harmful and we want to avoid. So here just some examples that where you get this kind of first order transition in the brain in several diseases, and you want to mostly avoid such kind of first order transition. And now let's see that what happens when I put adaptation in the higher order interaction. So in the earlier slide, I showed the state of art when you have adaptation in the pairwise. And here I am showing that when you put this kind of adaptation in higher orders. So without adaptation, pairwise lead second order. With adaptation, pairwise lead first order. Without adaptation, higher order also leads first order. So now if I have this kind of model, what do you expect? So now these are the results which is there. So now this is the result for this model. Okay. So now when beta was 0, there was no adaptation. So here this plot that is for K1, which is the pairwise coupling strength. And here it is R. I am sorry, this R is missing here, but always I am talking about this order parameter in y-axis. So you can see that as K is increasing, R is equal to 0 remains the stable solution until a critical coupling strength. And when there was no adaptation, you have a first order jump. Then the forward direction trajectories goes like this. And as you adiabatically decrease K, then you get this hysteresis, and here this experiences this kind of saddle node bifurcation, and it jumps back to the incoherent state. That was for beta is equal to 0, first order transition associated with the hysteresis. Now what happens as you keep on increasing beta, it means you are introducing adaptation in the system. So what very interesting phenomena which occurs, that you restores the second order transition. So you had the first order transition, but as you keep on, and we have an entire analytical explanation for that why we are getting such kind of second order transition to the synchronization. But as you keep on increasing this adaptation from the first order, now you can see you get the smooth. So from subcritical bifurcation, you get the supercritical bifurcation. And in between, you get actually the several interesting things which happens. First thing is the restoration of the second order transition to synchronization. And the second point is that we get tiered synchronization in the intermediate step, which I will also explain in the subsequent slides. So there are two different phenomena, and we have entire mean field Ott-Intenson, like entire very traditional analysis using Ott-Intenson method, which appeared in 2008. And we have, so this is entire thing is there in our paper, supplementary material of our paper. And we can actually find out the beauty of this entire Ott-Intenson approach is that this n-dimensional equation, like theta i's, which was n-dimensional, now that is collapsed into only one dimension, which is of the order parameters. So now we have the equation, the time dependent equation for the order parameter, which is the function of all the parameters, and it's a self-consistent equation because left-hand side and right-hand side, both side you have R1. But now this equation, one can do very simple linear stability analysis, and you can solve and you know the fate of the entire your system without actually demand of any numerics. So that's what this entire thing is about. And then we explain everything that why you get, and let me come to just one explanation that why we get this tiered synchronization. So as you keep on increasing, you can see here for higher value of K2, K2 is the higher order interaction. So as you keep on increasing K2, what happens that first trajectory, so this is a tiered synchronization here. So you get first second order transition, it means subcritical, supercritical bifurcation, and followed by some saddle node bifurcation. So, you know, there is some, you know, interplay between. So K1, which is the pairwise, tries to make the transition smooth, second order, and K2, which is leading some kind of frustration, is tries to make the jump, this first order. And because of this trade-off between K1 supporting synchronization, smooth transition to synchronization, and K2 along with beta, you get this interesting dynamics of tiered synchronization. How much time I have? Anyone has any idea? 7 minutes. Okay, so I can explain now this part actually bit more here. So you see, this is the entire phase diagram which I have plotted. This is K2 versus beta. So you can see that you have here first order transition when beta is very small. So for a smaller beta, still your pairwise interaction that is dominate, this higher order interaction is dominating for a small beta, and you get the first order. When beta is larger, you get this second order, and intermediate region, you get this tiered synchronization kind of thing. So, and here you can see the very beautiful picture of this is beta is equal to 0, first order transition, beta is equal to 2 in this line. First, you can see here it is supercritical bifurcation, is smooth transition, and then trajectory jumps. There is saddle node bifurcation which is coming, and this is the tiered synchronization which we witness in presence of higher order and adaptation. So let me here conclude my talk, and there would be some time for discussions and questions, I guess. So adaptation in pairwise and inclusion of higher order separately, they leads to first order transition separately. So pairwise, if you take adaptation in pairwise, it gives to first order. If you without adaptation, higher order, it gives first order transition. When you merge both, then you can lead to the new route of synchronization, that is a tiered synchronization, and it can restore the second order transition. And we provide a complete analytical framework. If anyone has any doubt, I would be happy to address that analytical framework to show the origin of this tiered synchronization and this second order transition to synchronization. This paper has been published, appeared online yesterday. And there are some other papers on simplicial complexes without adaptation. So Kuramoto oscillators on higher order network, we have written now several papers recently. And this is some advertisement of latest work where we have Kuramoto oscillators plus inertia plus higher order. And I think this is the first time such kind of framework has been analytically calculated. And this is here in this archive. So with that, I think I have one acknowledgement slide. So there's a lot of future directions. Of course, all the works, like whatever I have shown so far here in this slide and the previous work, whatever I have done is for all to all because analytics is easier. So one very straightforward extension is to include the network architecture there and then see that how inclusion of network architecture, different properties of network, for example, the small word properties of the network or this scale-free kind of thing, how it affects this adaptation scheme. And so far in this talk, I have only talked about the one cluster, but global synchronized state, but cluster synchronization is much more prevalent in real world system. So analyzing, these are the very straightforward extension of the work, inclusion of various other adaptive scheme. And this is my group at IIT Indore. And this is the Vajra project under which I am listing Stifno vocality. This is the scheme from Government of India, which sponsors, which facilitates such kind of long-term collaboration. And also, I would like to thank my Sir Power Grant. With this, thank you and questions.
If there are questions, I will come with the microphone. Questions or remarks? Like 1 minute.
So this tiered synchronization, you have proof for whatever values of K2. Is that correct? Or there is a minimal value of K2? This tiered synchronization, this new, does it appear for any value of K2 or you have a threshold?
Yeah, we should have one threshold because if K2 is very small, so yeah, there is a threshold because yeah, you should have some combination of K2 and R1 beta that can, so if you have a small K2 and large beta pairwise dominate, so you have a smooth second order. So you should have some threshold value of K2 after which tiered synchronization happens, yes.